Okay, guys, I think we'll start at time. But before that, let's make a little bit of a survey. How many of you guys ever used BERT as the model? How many of you guys pre-trained BERT? Okay, 2 of us. I need to apologize at the start. I'm native speaker Russian and I missed lots of English classes, so don't judge me hard for that. I think the presentation today will be not that technical as I wanted to be, but okay, I'll explain you what is the semantic search and how to build that. Okay, we have 1 minute less because it's a bit annoying when some guys come during the presentation, so we'll wait 1 more minute. So yeah. Okay, so there is 13:45. We gotta start, I think. My name is Vova. The full name is Vladimir, so you can call it me as you wish. I'm a research engineer in Unum, deep learning research engineer. And Unum is a startup where we first of all built databases. So one of the modern databases is vector database. The database where you can find the similar object by their vector representation. So that's why my talk for today is about the semantic search. There's lots of actually buzzwords here on the top. So multimodal, multilingual. So we will discuss today how to make your model multilingual and maybe how to make your semantic search engine multimodal. So we will see what is design, where is the encoding part of your queries and your database where you can try to search something. We'll discuss the indexes. Multimodality, multilingual models as well, and we'll speak about the future. We'll speak about a little bit of production, so how to build the efficient semantic search. Okay, so why we even need the semantic search? Why we need the more intelligent search than the exact or lexical search? Okay, picture the query. You want to find the fastest animal and you are trying to find the images. And actually the both answer are sometimes can happen. The fast snail. Snail is animal, obviously, and you can get it as a response, but that's not the way you want it. So you wanted to find the horse. So yeah, let's try to build the search a bit more intelligent than the lexical exact search. So the difference is that for the semantic search, you work not with the source form of data. You work with their representations or embeddings. So you want to try to put your query and all your database in some universal vector space such that your query and the potential answer or response are close in this space. The applications of it is wide. First of all, the web search. So Google, Bing, I don't know, DuckDuckGo, lots of others are already using semantic search. So you actually, by the textual query, can find the image, you can find the YouTube video, the piece of the audio, and the HTMLs. So there is lots of other implementations. One of that is the semantic search engine itself. You can use the semantic search for recommender systems because the problem is very similar. It's also used for question answering systems, not only actually open domain, but very others. Matching problem, the problem where you try to find the similar object in the internet. So for instance, in the Amazon, you find the good, and you want to find the similar in the eBay. So the semantic search is also helpful for that. And the conversational response selection, that is for my previous background, actually in voice assistants, textual assistants, you can use not only generative models, but the conversational response selections, that when you can have lots of potential responses for the query, and you're trying to find the most similar for that. So you have the pre-built database with answers. Okay, so what is the design? We can think of the semantic search with the two main parts. First of all, you should encode your data, your database, whatever modality it has. So you need to encode your database, put it somewhere. We will say build index, but we will explain what is the index a bit later. And the second part is the search itself. When you have a query, you already have pre-built vectors for your database. You need to encode your query as well. After that, you need to find the similar, I don't know, k nearest neighbor, for instance, in your database. So yeah, top k candidates. And after that, you will have the result for your query. So yeah, the part of encoding. So actually, lots of you may know that we can encode not only text, images, but we can encode everything. And what we are trying to achieve is that we want to encode everything in one universal vector space. So for instance, by querying the text, you are trying to find the image, or maybe a piece of the audio, or maybe code, or 3D objects. So yeah, today we will talk a lot about the textual queries, because it's you can find it, you can face it more often. So for the textual queries and textual data, mostly used sentence transformers. So the neural nets, when you're trying to encode, to have the embedding not only for the words, but for whole sentences. So for that, you just can put the pooling layer that will average the word embeddings after the encoding by the words. So yeah, here the link for the sentence transformers is somebody not familiar with that. Okay, but there is various training objectives for the sentence transformers or encoders. So I have actually the question for you guys. Can you say what is the problem with true-right objectives, with true-right architectures for the search? Why it can be complicated? Okay. Yeah, the right answer. If you have the query for the, let's say, cross-encoder, you need for every single vector in your database, you need to use your neural net. So it's complex, computationally complex. So you can't use it for retrieval, actually. So mostly for retrieval problem, B encoder is used, and not the whole architecture, but the only one part of that as an encoder, as a vector representation for the text. So yeah, why we need the two residuals? Actually, with the search problem, we sometimes trying to have two parts of the search process. The first of all is the retrieval part. So where we can find the top k candidates. So after that, let's say k is 10, we can use the different architectures. So like cross encoders or pool encoders, because it's computationally not that costly. So, okay. But we're not using the naive KNN implementation. Like, we're not trying to find actual k nearest neighbors. Sometimes for that we use indices. You can think of it like that is the data structures when you can find something more quickly than the naive implementations like naive KNN. So the LSH, KD trees, and HNL graphs as all data structures where you can find not exact KNNs, but approximate KNNs faster than in the naive approach. So yeah, there's lots of implementation of such algorithms, so such indices. You can find all of them in a repository called NN benchmark. There is the benchmark where developers was able to use CPU only, and they got as far as I know, contains like 1 million vectors with different dimensions, and there's lots of benchmarks such that where you have the queries per second and the actual measures of the quality, the recall. So yeah, you can find the best suitable algorithm for yourself, for your exact problem. And that is actually built very easy to use. You can just leave a few lines of CLI script, and that will work well. Everything is Dockerized and very suitable to use. Okay, so yeah, how to make your model multilingual and why we are curious about it. So the internet contact by languages actually looks like that. So there is lots of English contact in the internet, but not that a lot of users whose speaking language is English. So probably sometimes in, I don't know, in nearest future, the content will be more multilingual. That's why we all think about how to make our applications multilingual. So the search have to be also multilingual. So yeah, how we can do that? There is lots of approaches actually, one of which, if you have data for the pre-train in multilingual mode, you can do that. But in most cases, you don't have such, because the distribution between languages for pre-train sometimes like, I don't know, 80% English and 20% else, or something like that. So yeah, we can use some tricks, one of which is you can pre-train in high resource languages, few of them, I think Deutsch, Spanish, English, Mandarin, maybe. Yeah, and after that you will fine-tune low resource languages like Armenian. That's one of the approach. The second one is knowledge distillation. It's the approach when you're trying to make your student model multilingual, if your teacher model already multilingual. So you can take the big multilingual pre-trained teacher model and try to make a distillation for the student model that will make it multilingual as well. And maybe the student model will be, I don't know, less parameterized. The bad word. Yeah, my English. So okay, a few words about multimodal representations. So yeah, as I already mentioned, we want to have, for example, textual query and image as a result, or textual query and video as a result, or maybe mesh, or piece of the code. So how can we do that? What is the universal vector representation? Yeah, one of the most well-known approach is CLIP, built by OpenAI. That's the model which is actually has the similar structure as the B encoder. So that's dual encoder model. So you have the encoder here and here. So after you have the embeddings of the prepared data of images and texts, you'll have their embeddings, and you already know that this picture is similar with this text. And so as the ground truth, you'll have the identity matrix, and in the training process, you'll have the matrix where in this cell you'll have the similarity score for the embeddings. For instance, cosine similarity, or maybe dot product, or something like that. Yeah, and right picture is about the implementation itself, and actually you can see that the clip model is the retrieval model itself. But for the single query, you will have to encode every single potential responses that you have to. So every database. But you don't need to do that because you have indices, better indices. Yeah, the clip architecture. The encoder part for the text is the encoder part of the transformer. So it's BERT-like model, but not obligatory BERT. You can use whatever LM you wanted. So yeah, it's just transformer-based encoder part. And you also can make the knowledge distillation to make it multilingual. So already you have the universal vector space for multilingual text and images. So you can find through it to make it search. So for clip image encoders, in the original paper, the ResNet was used and the VIT, so the vision transformers. And the training objective is contrastive loss, the loss that was mentioned here. So the ground truth is identity matrix once again, and the similarity scores for as the predictions. Okay. Yes, that's what we want to achieve. So we want to have the textual query and the potential image. And in our universal vector space, we want to have it similar, between each other. In terms of, again, similarity measure, whatever you will pick, dot product, cosine similarity, anything else. So yeah, there is some tips and tricks that I already understand during the working with clips. The first of all is clip is very sensitive model. So try to keep your normalization layers frozen during fine-tuning, and actually sometimes during the late epochs in the pre-training. Always try to start with learning rates that low, and maybe keep it for the whole pre-training process. The clip is very sensitive for the data, so try to filter that as much as you can and properly shuffle. The original repository for the clip is not that good. There's no training scripts, no fine-tuning scripts, nothing actually, but only the architecture. So if you want to train or fine-tune the clip, try to use open clip implementation by some guys from Google, as far as I remember, and Stanford. And for fine-tuning or this knowledge distillation of your textual model, use sentence transformers. That was already mentioned before. And yes, clip training, pre-training clip, and also fine-tuning clip requires lots of GPU power. So be ready. Okay. What if we want to add more modalities? So actually, there is a lot of research about the approach for trained multimodal models for lots of modalities like text, audio, video, images. That's one of them. This the architecture from the paper called Audio Clip. The idea is actually the same. So you are trying to encode every piece of data you have, and you already have you already know that the picture, the textual description, and the piece of the audio are the same or similar. And where we can find that? We can find that from video. We can try to separate video by the audio, the picture, sometimes we have textual description of the segments of video and so on. But that's always challenging. So there is some papers. So one's called Audio Clip for video clip, the fantasy of the ML engineers. For Mesh, it's called Crosspoint. But there is also the problem, the source of the data, to find the proper data set to self-supervised learning. So you want to scrap internet in most cases. You don't want to build it yourself, or maybe human labeling. It's not that you cannot take the volume of the data set that you want to. So you need to find something. Okay, for audio, text, and video, and text, you can use videos, but not lots of videos. And for example, in YouTube, are properly labeled. Or imagine you want to find the data set where the where the meshes are textually descripted. It's actually very complicated. Okay, that is the example what we are trying to achieve. So as you can see here is the textual query, and actually lots of images as the results, like small round cat. And this query could be like potentially in every other language which is used to description for every image we have. But not only that, not only the textual query is interesting. In the fashion industry right now, every single application that are trying to make to give you a link for some, I don't know, Amazon goods or something like that with search are using the same technology actually. So you can put the image as a query and find the similar images, because sometimes it's hard to describe the goods. I don't know, the clothes, sneakers, how to describe it. It's complicated, so you can just take a picture and find similar. Okay, moving to production, yeah. In the previous PyData meetup, I was the speaker as well, and we actually, and I actually spoke a lot about the speeding up the language models. So that is the number. And you can take not only the BERT or the still BERT, you can try other models from sentence transformers, and you can try to speed it up. How you can do that, it's like a little bit a long talk, and you can see my presentation following the link. But to be short, it's always about the quantization, so you can use the different runtimes for that, like Onyx runtime or Tensor runtime, and other libraries to accelerate in GPU, on CPU, your language models. And that is crucial for semantic search because you need the high bandwidth. Okay, as I already mentioned, lots of database companies or startups right now are trying to make their own vector database, so the semantic search engine. And actually, we are trying to build every of the database. So the key value store, the document database, the graph database, and vector database itself also. And lots of modern databases already have the semantic search as the component. So when you're querying through the documents, actually sometimes the documents in the database itself has the index inside already. So yeah, I think that's pretty much it for today. So please welcome. Your questions are appreciated. Thanks a lot for your attention. Daniel?
Yeah, Vladimir. Sure. Hi.
Hi.
Okay, so my question is this. Is it my understanding correct that when you want to do a query against the graph database or document database or any of those representations for information, you create similar kind of indices and then you make query against them?
So you are trying to encode every single piece of data that you have in the universal database. So universal vector representation. Mm-hmm. So all the vectors you have, no matter what is the modality of the source data, will be held on the same, let's say...
multidimensional space.
Yeah, multidimensional space. So you can build index like through it to hold this data. So I don't think that for every single modality you'll have the separate index. This will be the mutual index for everything.
And you use something like R trees and so on for indices.
we used, or
You guys use.
we actually mostly we use the FAIS implementation
Oh,
of
right, FAIS.
HNSW with some quantization. So yeah, lots of indices, implementation of the indices right now not work with the bare vectors that you have after the representation learning. It's mostly quantize the vector or maybe trying to lower the dimension of the vectors and the so-called pre-processing. And we use the HNSW with some pre-processing.
See.
And lots of them actually already pre-built in FAIS. So FAIS is a great repository, guys. There is also not only the CPU version to the indices, but also the GPU version. And in the repository big INN benchmark, you can find lots of implementations for GPU versions. And actually, I think one of them only open sourced. It's the FAIS.
Yeah,
in FAIS distributed.
Yeah, I mean, we at Tipalov, we also use FAIS
Yeah,
for semantic search. Yeah, and one more follow-up question, if you don't mind.
Yeah.
Do you have any idea or desire to add reasoning on top of your graphs? So, I mean, when you do some kind of semantic search, it's one story because you'll find objects that mostly correspond to the queries you got in the beginning. But if you represent data as a graph, one of the benefits of the graph is you can add ontology on top of it, and then you can do reasoning. So, do you have any desire to build something like that into your system?
We have desire, but we didn't got the already built solution for that. So we we are looking forward to the research about that.
Okay.
So, yeah.
Thank you so much.
Thanks a lot.
Thank for a great presentation. Did you use open source datasets to train systems?
Yeah. Okay. We actually had the chunk of the command crawl, so we tried to filter it by ourselves and try to train it on it. But actually, mostly right now for pre-trained multilingual clip that I'm doing right now, actually, we use the open source dataset called Lion. There is two versions of it. One of the 4 million pairs for English only, and in the last releases, like 2 months ago, 3 months ago, they released the dataset with 5 billion pairs, which half of it is multilingual. So right now we close to download it, and I already tried to pre-train on chunk of it in let's say 5 terabytes. 3 terabytes chunk of it, and I pre-trained the multilingual clip, and it's close to good enough actually. In sentence transformers, you can find multilingual clip as well, but it's not pre-trained. It's knowledge. It has the knowledge distillation, and the metrics are close. But in my feeling, that more data you have, the more data you show to the clip, the better the results. So yeah.
Is it about pairs, images, and sentences?
Yes. Yes.
What about audios?
For that, there is not lots of open source data sets, and we actually right now we didn't add in the production version of algorithm the third modality, and we also it's more like research, and the matrices is not that good, and we think actually maybe the whole architecture is not appropriate for 3 and more modalities. So that for audio and text, you can use podcasts, actually. That's
audio set is contain 2 million audios with videos.
With textual captures. Yeah?
No, with images.
With images.
But you can train with pairs, images,
and
audio.
Audios? Okay.
And
in the audio text separately, you can train. Yeah. There is some data sets, but 2 million pairs, it's, in my point of view, it's not enough. Because for text and images, for training the clip, they got 400 million pairs in original paper, as far as I remember. And now there is open source data that has 2.5 billion pairs.
If you can, for example, extract from YouTube pairs, audios, and frames.
Yes, but you need to filter this data properly because that's the textual description, for instance, mostly incorrect.
No,
Without
description.
Just only images and audio.
Да, ну,
Yeah, okay.
Просто сложно. Ну вот, в общем, есть пары аудио, есть текст, пары и изображения. Но если обучить на парах изображения и аудио, это же можно будет потом использовать и для текста. То есть, потому что будет по Constant Similarity аудио близко к изображению, и также будет близко к тексту, получается. Вот такая идея.
Okay, that's actually not work like that, I think. So I didn't find the papers that you can train text, image, and image audio separately, and after that you will have the whole, good representation for the text and audio. So I think it should be, I'm sure they should be trained like at the same time. So you need to label data for all the modalities you want to see in your universal vector space. Maybe I'm incorrect, but show me the paper.
I would try maybe
Okay.
The property of transitivity, transitiveness.
Yeah, I understand, but I think you will train different spaces for different pairs. You see, and after that you need to match it. So maybe it will work if you will add some dense layers in the head of your encoders and train it to somehow match your vector spaces.
No, if
but in the bare implementation, I don't think that works well.
Image model is fixed, for example.
Okay.
Is fixed during training on pairs, audios, images.
Okay. But I don't see the connection. I cannot follow that. So.
No, if more model parameters are fixed and not changed, I think.
Yeah. But vector spaces would be different. If you train it in the pairs of modalities, it will be different, and you need to somehow match that. Yeah, or I think so. I think so. Okay.
Sorry, can you explain a bit more about this teacher
and
student?
The knowledge distillation.
Yeah.
Okay. I'll try to elaborate. Actually, the distillation somehow, most of the time, used to make your model a bit less weighty. So you are trying to use, as a student model, the model with less parameters. But that's not the only case. Sometimes distillation works to distribute your knowledge from the teacher model to the student model, but it's, the volume of the models are the same. So you can actually, by the distillation, transfer the knowledge. Imagine the teacher model is sentence-based model, and the student model is word-based model. And by this distillation, you will make the sentence model sentence-based as well. So it will embed the sentences better. So the same idea is for the languages. So you can try to encode. So you can try to transfer the multilingual, I don't know how to say it in English. Okay, the multilingual skill from the teacher model to the student model by this distillation. So you'll have the mutual loss for both models, and by that your teacher model will learn the multilinguality as well. Is it understandable?
So when you say knowledge distillation, do you add a reasoning layer onto it, or it's just based on the indexes?
Okay, I see. Actually, in code, in the architecture, you add the pooling layer sometimes and the dense layer in the top of the models to the student model to teach something. But you don't keep your model frozen, so the parameters are not frozen. So yeah. Any more questions? Yeah.
So the clip architecture that you described, it only allows, as far as I understand, 2 or 3 modalities, right? Do we have any architectures that scale well with more modalities?
So I'll say that there is lots of research about that. The model's called. Let me remind that. Okay, there is the models which are trying to achieve the multimodal training for lots of modalities, for lots of tasks, and there is some successes. But I personally didn't see the good implementation of it. So maybe in some private data sets in big companies it works, but in open source I thought only one repository related with, or maybe 2 repositories with related to 3 modalities, and lots of 2 modalities like text and images. There's lots of good implementations, but for 3 and more, I'm not sure. But we are working on it. So, yeah.
Thank you.
It's called fundamental models. You can try to find it in papers with code. There is lots of research. Okay. Here, you want to ask questions? Here's the guy. Yeah. Thanks.
Yeah, thanks a lot for the talk. I apologize for a stupid question because it is caused by my lack of experience in the field. So, as you said, when you encode the data from different modalities into single vector space,
Okay.
you use different encoders, specialized encoders. And so I imagine if you want to achieve like consistency between the different modalities, the encoders have to have some consistency, right? Is there like a well-established way on achieving that aside from picking the correct data, or?
The consistency, what is the consistency? What do you mean?
I guess the encoders, for example, the BERT encoder on the textual side, the resident on the images side, you can take them pre-trained, right? But
yeah.
Some fine-tuning has to be done, or the training.
Okay. Yeah, I need to explain something that. Okay, you can take the pre-trained models as the initialization of the clip, but clip itself also had the pre-training. So actually, you can think about it as a fine-tuning, but you'll have lots of data, lots of epochs, and lots of time to train GPUs and so on and so forth. So that is actually the pre-train itself. The contrastive loss is lost for you can call it fine-tune, but actually it's the pre-training. So there is lots of data, lots of steps of learning, the scheduling for learning rate, and so on and so forth. So yeah, to achieve this consistency, as far as I understand what you mean, you make the pre-train for the clip itself.
Yeah.
Whatever you initialize the clip from.
Thank you for your presentation. I wanted to ask you, is there any way to, so recently I was reading that like Meta AI published that they have this NLLB model, No Language Left Behind. It's a they open source their text encodings, and they say it works on 200 languages. So even low resource languages are included. I wanted to ask, is there any way to use just these text models to make it multimodal somehow? I don't know, for example, using...
As a teacher model, to have this meta.
Yeah.
Yeah, that's possible, but the problem, I think, that this model is too weighty.
Oh.
This doesn't fit the, I don't know, any GPU cluster that is exists in Armenia, for instance. So as far as I remember, the Meta AI model is really huge, very large model. So I am personally used like a little bit less parameterized models like multilingual BERT or maybe T5 with base version of the models. But yeah, you for sure can use that because it's easy to calculate the MSCI or maybe some other contrasted class.
Okay, thank you.
So you can take whatever you want. Okay, since there's no other questions, thank you all for the attention.